The videos today, we're gonna work on something together. What I want to do is talk about weight, which is something that we went over last week, but also use that to introduce what are called quantitative force diagrams. So when we talk about quantitative, what we mean is specific values. So in the past when we did qualitative force diagrams, when you guys were drawing the little arrows to show all the forces acting on an object, all you had to do was just draw arrows and kind of what direction they were going in. That was just, like I said, qualitative. It wasn't how much. That's what we're moving towards now, is where you need to be able to explain how things, or how much force is acting on an object. So here's what I want to do. I want to make sure that today you know how to calculate weight using that idea of mass times the acceleration due to gravity. And also just go over how to actually calculate those different forces that are occurring in that force diagram and use it to find other forces. All right. So here's just some things that I want to review that we've gone over, but just want to make sure that you understand how this works. Remember when we did the bowling ball and used the broom and got the main idea behind that was that I wanted you to be able to understand that objects only accelerate when there's unbalanced forces acting on them. So things only speed up, slow down, or change direction when you have those unbalanced forces. When they're balanced, there's no acceleration, meaning it's going in a straight line at a constant velocity, or it's just not moving. We also, last week, you guys figured out that the force of gravity that's acting on an object, that equals the object's mass, which is in kilograms, multiplied by little g. Okay? So little g is just the acceleration due to gravity on whatever planet or wherever you're at. In our case, little g is about 10 meters per second squared. But if we go up to the moon, and that's something we talked about last Thursday and Friday, if you go up to the moon, little g there is about 1.7 meters per second squared. And the last thing is this whole idea of newtons. Okay? Force is measured in what are called newtons. So newtons are how you measure pushes or pulls. And what 1 newton equals is it's how much force you would have to push something in order to get a 1 kilogram object to accelerate at 1 meter per second squared. So it's kind of like one newton is about the same as like lifting a Big Mac above your head, for what it's worth. All right, so those are the things that I just wanted to go over. Here's the plan for today. All right, this is Cruz. Okay, this is my 5-year-old. He has no filter. All right, so whatever is on his mind, he says, and he's very blunt about things. And so it's that time of year when I'm kind of looking at stuff and trying to figure out what to do next. And anyways, yesterday, sitting down on the couch with my wife, and we happened to get out our wedding pictures. Now, we were married over 15 years ago. That was back before kids. And here's just something you have to understand. Your parents were a lot more fun before you came along. And as much as they love you, as much as they are glad that you are in their lives, you have sucked every bit of energy out of them, all right? And I am reminded of this daily, because as soon as I walk in the house, my kids just like suck all the energy out of me. So when I used to be spending time like running and exercising and doing other stuff, I'm like sitting on the couch trying to stay awake. All right, and that's just how it works. So as that has happened, I have lost hair. I have also gained weight, and as I'm sitting there on the couch with my wife, looking at these wedding pictures, Cruz comes barging in, and he's like all elbows and like, everybody get out of the way, I have to see what's happening. And he goes in there and he looks, and he sees a picture of me and my wife, and he says, "Mommy, who's that man with you?" And I'm like, "Cruz, that's me." "No, it's not." "Cruz, that's me." "No, it doesn't look like you." And once again, that was back when I had a lot more hair and weighed about 30 pounds less. So he was not convinced that that strange person in the picture was actually me, which has me thinking about, okay, it's that time of year. I really need to get back in shape again. So how can I do that? And that's when it's bad to watch infomercials, okay? Because they prey on people like me. And that's where this whole thing comes up, the whole P90X, okay? So P90X is geared at old people who are out of shape and need to get back into shape and need to relive the glory days of when they were stronger, actually had six-pack abs and all of that other stuff. Enjoy it while you can, all right? But so I'm going to start in on another round of P90X. Hopefully it lasts more than 5 days this time around. But here is what they do. So the 90 stands for 90 days. And you're supposed to do these workouts every day for 90 days. And if you do that, they promise you that the before picture and after picture will look a lot different. All right, and that's kind of how they sell you. So we are going to use this little trip with P90X to kind of figure out some things with weight and force calculations. So here's what we're going to start out with. So thinking back about what we've talked about, like I said, the thing that we need that you do with P90X is they have you take like the before picture and the after picture. And the whole thing, if you've ever looked at any before picture and after picture, you'll always know, or you'll always see that the before picture, they're always like, and then the after picture, they like have a tan and a new haircut and they're smiling. And it's better light and all of that stuff. So that's what they make you do, is they make you do like the before picture, the after picture. They have you weigh yourself. They have you do all of these push-ups and other things like that so you can see progress throughout the 90 days. So here's what I'm wondering. So think back to what we've talked about here. What's my weight in newtons if I have a mass of 93 kilograms? How would I figure that out? Simon, how would we do that? Okay, so what's the equation that we're using? Okay, so the force due to gravity on an object. Okay, that's the same as weight. All right. So weight equals the object's mass, and that has to be in kilograms, multiplied by little g, which is the acceleration due to gravity. So here on the Earth, let's just make the math easy. It's normally 9.8 meters per second squared, but we're going to say this is going to be 10 meters per second squared. So if I want to find my weight, if I want to find that force due to gravity of me sitting up here on Earth, I'm going to take my mass, which is going to be 93 kilograms, and multiply that by little g, so 10 meters per second squared. And we end up with a weight of 930 newtons. So that's how we would calculate my weight. So think about this. So weight it's a force. It's a push or a pull. So as I stand on that scale to figure out my weight, I'm pushing down. All right. And the amount that I push down is what moves the little needle and gives me the how much I weigh. What would happen if I went up to the moon to do that? Does my mass change on the moon? No, mass stays the same. Does my weight change on the moon? Yeah. Why is it that I'm going to weigh less when I stand on that scale on the moon? Why is it that I weigh less if I'm still the same size? Good. So weight depends on gravity, and gravity on the moon is about 1/6 of what it is here on Earth. All right. So that's a good one to know, how to calculate mass. So here's the other thing. Okay, one of the things that they have you do a lot in P90X are pull-ups or chin-ups. So this is how they make their money. All right, by selling you all of these extra things. So a long time ago, I broke down and bought one of these. And go down in my basement, and you have to like put it in the door jamb. And I'm just, one of these days, my wife is going to be sitting upstairs, and I'm going to be downstairs, and she's going to hear this crash, and I'm going to be like on the ground, it just like with a broken leg or something because the wall just couldn't handle me. All right. So, anyways, that's your chin-up bar. And of course, it says get absolutely ripped because that's how they sell you lots of extras. But here, let's use that idea of the chin-up bar. Could be.
Injury prone.
Yes. People that are having their midlife crisis are extremely injury prone. So here, let's take a look at this. So think about if I'm doing my pull-ups here. So here's the door, here's the chin-up bar that sits there, and here's me, here's Mr. Spencer. Okay. And here's what's happening. I'm sitting there, I'm hanging from the pull-up bar, trying desperately to actually pull myself back up. Okay, so shaking arms and everything else like that. And here's Cruz. Okay, he's probably eating something with sugar in it, all right, because that's just how and what he does is he thinks it's hilarious that when I'm trying to do this, when I'm struggling just to do like one pull-up, he runs over, and he grabs my leg. All right, so here's Cruz thinking it's hilarious to grab Dad's leg and pull on him while he's struggling to do one pull-up. I'm not the greatest artist in the world. All right. So let's think about this. Let's get rid of Cruz here. All right. What's the total tension in my arms as I hang from my pull-up bar? Let's do it this way. Let's draw a force diagram. So if I'm sitting here, if I'm just hanging, trying from the pull-up bar. Am I speeding up, slowing down, or changing direction? No. Okay, so if that's the case, what kind of forces do I have? Are they balanced or unbalanced? Balanced, okay? So what forces are acting on me as I hang on the pull-up bar? Gravity, okay, so we have the force of gravity on me by the earth. What balances that out? Tension. So where is the tension? On my arms as they're shaking. Okay. So so I also have this force of tension on me from my arms. And if I could spell arms, that would help. All right. Now, if I had drawn this the right way, how would this force compare to this force? They would be the same. What would be the same about those two forces? Because there's some things are the same and some things are different here in this example. You all started looking at your desks. Don't make eye contact with Mr. Spencer. So what stays the same with these two forces? So remember, force is a vector, and vectors have magnitude and direction. So if we have magnitude and direction, so we're talking about magnitude or direction. Which one of those stays the same? Yeah, how much? Magnitude stays the same. So these forces, the how much is the same. What's different about them? Direction. So one's going this way, the other one's going this way. So they're going in opposite directions. So how on earth am I going to figure out what the tension in my arms is? So you're saying, wouldn't it be the same as gravity? What do you mean by that?
So it would be 9.8. Like, because the force of gravity is 9.8, so what would be the tension?
Okay, so 9.8 is the acceleration due to gravity. But how do we use that to figure out force due to gravity? So how do you figure out the force due to gravity of an object? Simon, how's that done?
So, if you said that you weighed 930 newtons,
Yep.
and that's the force that's pulling you down, and we said that the force pulling you up is the same magnitude but different direction, then it'd just be 930.
Exactly. All right, so what he's saying there is the force due to gravity, that's my weight. That's my weight, Earth pulling down on me from because of my mass. All right, and you guys just, in the last one, you guys just figured out that I have a weight, or a force due to gravity of 930 newtons?
Yeah.
Okay, so this is 930 newtons. Gravity's pulling me down with a force of 930 newtons. So in order to have that be balanced, what keeps me from falling? The tension that's in my arms. So that is acting at a force of 930 newtons. Could you please stop? That's like the third time you've done that. But 930 newtons going this way. All right. So hopefully that makes sense. When I'm just hanging there, the total tension in my arms is going to equal my body weight that's pulling down. So when Cruz goes and grabs onto my legs and starts to swing, what happens? What do we start feeling in my arms? I feel a lot more tension, okay, because I've got that added weight pulling me down. So here's the next thing, okay, is I've got to get used to box jumps. How many of you have done box jumps before? They're great, okay? Like if you're looking to get some hops, okay, box jumps are fantastic. The only problem with box jumps is that when you get tired, what happens to the height that you're able to jump? It gets lower, and when the box doesn't change, so that means that you end up like ramming your shins into that part. And I swear that whoever made these things are like sick and twisted, because it's just, these end up being sharp. They try to... They try to do, it's sharp, and it seems like I always catch the sharp piece with the like slivers and things like that. So you get blood running all down your shins and stuff. But at least it makes you a really good jumper. Anyways, so think about this whole idea with box jumps, of jumping up and landing on top of the box. So if I want to draw a force diagram of the box with me on top of it, what's that going to look like? So here, I'll draw. Okay, so here's the box, here's the ground, here's me with ape arms. Happy that I made it up on top there. Okay. So we're going to do just the box. Hey, could one of you close the door there before it gets loud? So what forces are acting on the box? Gravity. Okay, so the good old force of gravity on the box by the Earth. And then what else? Okay, so I'm just going to call that my weight. All right. So then I've got the force of, we're going to call that weight on the box by me. What other forces do I have acting on on the box? The normal force. So which way is the normal force? Up. Okay, remember that's that line, that force that's perpendicular to the surface. And we've got the ground here, so we're going to have the normal force on the box by the ground. So if I go and take this and redraw this, okay, so here I have my dot, and that dot represents the box. Let's take these and put them over here. So I've only got ones that are going up and down. So which ones are going up? The normal force. All right, so I have my normal force. Once again, it's acting on the box by the ground. And what forces are going down or in the opposite direction? Okay, so we've got my weight on the box by me, and we also have force of gravity on the box by me. So how should these forces relate to this force? Now when you say they should be the same, what do you mean by that?
They should. Yeah.
Say that again? They would cancel each other out. So in order to cancel each other out, what does the magnitude of how does the magnitude of this one compare to the magnitude of this one?
That plus that should.
Okay, so if I add these two together, if I take the force of my weight plus the force of gravity, that is equal but in opposite direction of the normal force. So I could redraw that in a way as the normal force. And if I drew this the right way, how would this one compare to both of these added together? They'd be equal. So what happens to the normal force if Cruz decides to run and jump up on this? He wouldn't jump into it. He would run into it first, try to knock me off, and then like stumble down and then like crawl up. But once he's sitting on top of that, what happens to the normal force? It goes up. Okay, so the ground has to push back more because there's more force pushing down on it. So let's take this another step. So with this in mind, if the box weighs 150 newtons, how would you find the normal force acting on the box by the floor with me standing on it? So add mine. So what was my weight? 930 newtons. Plus the box's weight, or the force of gravity acting on the box, which is 150 newtons. You add these together, and that gives you this one. So 1,080 newtons.
Is that a W or an F?
Which one? This right here?
Left one and the next one before that.
This one?
Diagram before that on the left.
Yes, that's a W. We're saying that's my weight. All right, so that's how you would get that. All right, one last question before we do some of these together. How would you find the mass of the box if it has a weight of 150 newtons? And don't say weigh it.
That's weigh it.
How do you find the mass of the box? Yeah, because remember we've got so weight equals mass times acceleration, or mass times little g. So if we know that the weight is 150 newtons, we're trying to figure out the mass. Little g is 10 meters per second squared. Well, I just divide each side by 10, and I get the mass being about 15 newtons. All right? So, what time is it? Okay. So here's how we're going to do this. I've got one more thing that I want to do together just to make sure that you understand this, but we'll have the quiz on this first thing tomorrow. So let's do this. Go ahead, grab a whiteboard and marker for your table. All right, so markers are up here. Whiteboards are back there.
Your clock's wrong.
Yeah, it's like an hour fast. Or like an hour and 5 minutes fast. No, I never use it.
Dave is my fave.
You don't have to put up with that. So here's what I want to do. I want to do some practice problems. Just make sure that you guys all understand how to do this. And of course, there's a little story here. Okay, I spent my first 2 years teaching out in Utah at a place called American Fork Junior High. And so this guy right here, this is Kevin. Okay, Kevin was my mentor teacher. So when I started teaching for the first time, it was in his classroom. And this is what you guys got to understand, okay? You guys are really, really intimidating. Like 30 high school juniors and seniors staring at what it's like for a first-year teacher. It's really, really scary. We try to fake it as much as we can that we know what we're doing, but we don't. All right. But anyways, so when I was a student teacher, when I was practicing on his class. The very first time I met him, it was the day before Christmas break. And I was going to start working in his classroom after Christmas. And they wanted me to meet him and kind of get to see what the class was like and all that fun stuff. Anyways, I'm sitting down in the office waiting for Mr. Dickerson to show up. And all of a sudden, the door opens. And on a unicycle, is this guy in green tights, Christmas boxers over those, a red long sleeve T-shirt, and Santa suspenders. And once again, he's doing this on a unicycle, and he's like, "Hey, are you Dan?" And I'm like, "Yeah." He's like, "I'm Kevin. Nice to meet you. Come, let's go up to my room." And this was just the kind of person that he was. It was always about making an entrance and doing crazy things and stuff like that. And he was just this amazing science teacher that all the stuff you guys are learning from, or all the stuff we try to do is me trying to be like him. Anyways, along with being this amazing science teacher, he had a part-time job. He was one of these people that didn't need to sleep. He was an EMT, so an emergency medical person, all right? So what he would do is whenever there was an emergency, he'd have he'd have an ambulance parked in his driveway, and he would go and take care of stuff. So he would always have these amazing stories. But his specialty was rescue, cave rescue, because out in Utah, you're right up next to the mountains, and you've got lots of caves, so you'd get people that would get stuck in these caves, and he'd have to go in and get them out. So one day in class, he came in, he's like, "Dan, I can't be here today. Somebody crashed a plane into the side of the mountain, and I have to go rescue them, or I have to go. They have a search team that needs to go do this." So he came back with lots of stories about what he found during the plane crash. But anyways, so just the other day I was looking through and trying to find some stuff for today's lesson, And I found this article about Kevin in 2012 and a rescue that he did. This is what's called Provo Canyon. So the city, Provo City is right down there in the valley. And then you have these Wasatch Mountains that are up to about 11,000 foot elevation. So this is floor level is about 5,000 up to about 11,000 feet. So it's absolutely beautiful. I would go running there all the time and lots of cool stuff. And whenever I would go running down Provo Canyon, you would always see these people that were doing base jumping, meaning they would go and climb up as far as they could and jump off and then go parachuting through the canyon. Sometimes it works, other times not so much. Well, what happened was, this article that was about Kevin was that somebody had gone base jumping in Provo Canyon, and I think what had happened is there was a big gust of wind that came, and after they jumped out, so you jump out, you fall for a while, and then you put out your parachute. Well, that gust of wind came along, took them and slammed them back into the wall, back into the cliff. So they slam into the cliff and then starts to fall down alongside the cliff. And the only thing that kept this person from crashing into the valley floor was his parachute. So here's the guy right here. I don't know if you can see him there or not. But up here, the parachute, the only thing that's holding that, or what that parachute grabbed onto, was a rock about the size of a basketball. So fortunately, it grabbed onto something. The bad part is in a mountain, things are always falling. So that wasn't very stable. And Kevin's job was to go in with his team and rescue this guy who was stranded about 700 feet off the valley floor, being held only by his parachute that was caught on a rock above him. Very long story to get to this. Let's say Kevin has a mass of 83 kilograms. What's his weight in newtons? Do that on the... Show me your work. So what are the units on per second. Yeah, meters per second. Yeah, let's use a little g of 10 meters per second squared. Why are you being so mean?
They were yelling at me, Zach, you're being lazy. We're doing 9.8. Go.
What you looking for? You're just wandering? All right. So just going around, it looks like everybody got 830 newtons. All right, if you got 830 newtons, good. Weight is equal to mass times the acceleration due to gravity. So 83 kilograms times about 10 meters per second squared gives you 830. Okay, next one. Now that was Kevin. Let's look at the base jumper. Let's say we've got a base jumper. He's hanging onto the side of the cliff by just his parachute. If he has a mass of 68 kilograms, what's the tension in the parachute? What I'd like you to do is draw a force diagram and then show your work.
680, right? Because,
Yeah.
so this one's 680. Can I go to the bathroom?
All right, so what's the tension?
That's what I was confused about. 'Cause at least maybe I was doing time. I think didn't you write that it was the same for both, and that's where you kind of lost me.
So in this case, so let's go through this together. In this case, here's the guy. All right? What are the forces that are acting? Well, first of all, is he accelerating? No. Okay, he's just hanging there. So what are the if he's not accelerating, do we have balanced or unbalanced forces? Balanced. So what are the forces that are acting on him? Okay, so we have the force due to gravity and the force due to tension. So they're going, force of gravity is pointing down, the tension is pointing up. So if these are balanced, that means they need to cancel each other out. So if they cancel each other out, that means they have equal magnitude, but are pointed in opposite directions. So how could I figure out the force of tension?
The same as the force of gravity. So it's
Yep, it's the same as his force of gravity of him hanging there, so or his weight. So in this case, his weight is going to equal 68 kilograms times the acceleration due to gravity, which is 10 meters per second squared. So this is going to be 680 newtons pointed down, and that means that the force of tension is going to be 680 newtons going on. So what would happen if my 5-year-old, Cruz, decided to go jump on his leg? What's going to happen to the tension? Yeah, the tension's going to go up. And there's a reason why I have to keep my kid away from tall buildings and other things like that. All right. Next question. We're going back to Kevin. Okay, back to Kevin. We've already figured out some things about Kevin. So we're going to assume that Kevin rappels down to a nearby ledge during the rescue and then sits down on a rock to rest. Okay, so he's sitting there.
just a sec.
Wait a second, all right? So that's true. I never thought about that. Well, hey, if you're dumb enough to get yourself in that position, you got it. All right. So here's the ledge. Here's the rock. And here's Kevin sitting on the rock eating a sandwich while he hopes that the guy doesn't go falling to his death. Anyways, I shouldn't joke.
Guy's probably knocked out anyway.
So if the rock weighs 450 newtons, what's the normal force on the rock with Kevin sitting on it? So what are the forces that are acting on the rock? So we have the force due to gravity, which is the same as weight. Okay, so and what is the weight of the rock? 450 newtons. And we have Kevin, the force of Kevin. All right, what's Kevin's force? What was it, 680? Okay, 680 newtons. So what's the
830.
830?
Oh.
Yeah, that's right, 830.
Oh, yeah, that's for the
830.
and the
What?
normal of the lead.
Oh, okay.
Sorry, So then, what other forces are acting on this? The normal. So which way does the ledge go? Up.
Well, maybe.
So force of normal, so that's going to be 450 newtons plus 830 newtons. All right. Man, this goes fast. Okay. What's